For centuries, humans have wondered what matter is composed of. Many today know the atomic theory given by John Dalton in 1808, and for nearly a century after, the atom was accepted as the most basic building blocks of our universe. After all, the word atom is derived from atomos, indivisible. However, after the discovery of electrons, protons, and neutrons, we know more about the atom, and we know it's not truly indivisible. But even these tiny particles were not in fact the fundamental building blocks of matter. Many questions about the nature of forces remain unanswered until the early 1970s, with the establishment of the Standard Model. The Standard Model of elementary particles classified truly indivisible particles, at least to our current understanding, into two basic groups, fermions and bosons. Fermions contain the quarks and leptons, which build matter, and bosons contain the gauge boson and Higgs boson, which carry forces. First, let's talk about the fermions. The fermions contain the two basic groups called quarks and leptons, and within each group there consists of 6 particles, which are related in pairs, or generations. The lightest and most stable particles make up the first generation, whereas the heavier and less stable particles belong to the second and third generations. And all stable matter in our universe is made up from particles that belong to the first generation, and heavier particles quickly decay to the more stable ones. First, let us begin with the quarks. They are in generations of up-down, charm-strange, and top-bottom. The up quark and its counterparts have charges of 2/3 of an electron, and the down quark and its counterparts have charges of -1/3 of an electron. Quarks can be either left-handed or right-handed, depending on their direction of spin with respect to their direction of motion. The left-spinning up and down quarks can transform into each other with the interaction of weak forces. Oddly, however, right-spinning quarks are unable to transform into each other. Quarks also have a property known as color. Quarks all start with a certain color, either red, blue, or green, and different color quarks must be binded together to create composite particles, which are colorless. However, this color is not the color that we sense. It is an abstract concept that describes a quark's interactions to strong force, the force that binds quarks into composite particles such as protons and neutrons. Next, let's talk about the leptons. Leptons are in generations of electron and electron neutrino, muon neutrino, and tau neutrino. Leptons have mass but are colorless, thus they do not interact with a strong force. Electrons have a charge of -1 and neutrinos have no charge. As with left-handed up and down quarks, left-handed electrons and neutrinos can transform into each other via the weak interaction. However, right-handed neutrinos have not been seen in nature. Because neutrinos have no charge, this means that they only interact with other particles via gravity or the weak force, which means that they scarcely interact with anything at all. In addition, neutrinos have masses so slight that even a 9-volt battery has enough energy to accelerate them to 99.7% of light speed. Talk about a particle accelerator. It is a small wonder that neutrinos can pass through the object's size of the Earth as if it wasn't there. Now I will be talking about the bosons. The bosons contain the gauge bosons and Higgs boson. The gauge bosons consist of gluon, photon, Z boson, and W boson. Gluon is a carrier of strong force. They have a combination of 2 color charges and interact with each other and the quarks through the strong force, forming a gluon field which keeps the composite particles together. The strong force is about 2 orders of magnitude stronger than the next closest force, electromagnetic force. The photons carry electromagnetic forces, and they interact with all charged particles. The W and Z bosons carry the weak forces. Remember how the up and down quarks transform into each other? They undergo this transformation through the exchange of a W plus or W minus boson. However, we know less about the Z boson. It is uncharged and seems to merely cause the loss and gain of energy and momentum. Finally, the Higgs boson particle. This particle, since its discovery in 2012, has been hailed the God particle. The Higgs boson particle gives an explanation for how particles gain mass, and it joins the left and right spinning particles together. As a particle such as an electron moves through space, it constantly interacts with the Higgs bosons, excitations of the Higgs field. When a left-handed electron bumps into a Higgs boson, the electron might ricochet off of it in a new direction and become right-handed. Then it can bump into another Higgs and it becomes left-handed again, and so on. These interactions slow down the electron, and that's what we mean by mass. In general, the more a particle interacts with the Higgs boson, the more mass it has. That's about it for the elementary particles. However, I have only covered about 50% of the standard model, the other half being antimatter, which have similar interactions as ordinary matter. It's kind of like the evil twin. And it's basically, instead of the up quark, you have the anti-up quark, and instead of electrons, you have positrons, but they all interact in very similar ways. At least as far as we know, that is, and we don't really know that much about antimatter yet. Now, I'm going to talk about some limitations to the standard model. For example, although the Higgs boson particle explains how quarks and electrons gain mass, it cannot explain how neutrinos gain mass because, well, there's no right spinning neutrinos for the Higgs particles to interact with. And also, the electromagnetic and weak forces are proven to be of the same origin, known as collectively as the electroweak forces. However, there's nothing linking the strong force to this group, and the case is even worse for the gravitational force and dark energy, which have no explanation in the standard model at all. But even just with the particles we have concrete evidence of, there seems to be problems left and right. In fact, what got me interested in researching the standard model was due to a huge news story last April. A study published in Science studied the weight of the W boson and found it to be 77 megaelectronvolts higher than expected. That's an entire 0.1%. But it seems to blow up the world of particle physics. Even Nature published an article titled, "Particles' Surprise Mass Threatens to Upend the Standard Model." But this is not the first time the standard model has been put into question. In fact, the standard model has been on the verge of death for a long time until its saving grace, the Higgs boson particle, was discovered. And we can see the effect it had because Peter Higgs got the Nobel Prize just 1 year after its discovery. Things on the frontier of science is always changing, and many of these changes seem to topple the tower of the standard model. It has never failed after some 50 years, always being fixed just in time by another edition of new discoveries. Therefore, I am optimistic that this will just be another of our stepping stones for a revolutionary discovery. It is important to remember that discoveries in science has never been easy to accept, certainly not when the heliocentric theory was proposed, and certainly not for anything in the modern day. But through the relentless effort of humans on the pursuit of truth, we have overcome countless obstacles. Science is about the cold numbers, but it's about so much more. It's about the wildest of imaginations, and it's the courage to imagine. The courage to step into the void and leave if only the faintest light for others to follow. This is nothing short of courage for Peter Higgs to put forth his imagination for the Higgs boson particle in 1964, and for countless other scientists out there. The world is so much more than what we have gathered through our some 200,000 years on Earth. And to all current and future scientists, remain curious and be brave. Thank you.